Hi, everyone. Thanks for the invitation. It's great to be here. Today, I'm going to talk about a topic that is fairly new to me, but has some connections to some of the topics already throughout this workshop, including this one. So this was work with a number of collaborators, and in particular, I want to give a shout out to the students who worked on this, who visited us from Singapore, Charlie, who's in the audience today, and Shuai-Chi. So data valuation is an area of research that tries to study or propose metrics for evaluating how much data is worth. And there's a wide swath of literature on this, and typically for the purpose of designing data markets. So the idea is that you would have users who are contributing data. You want to know how much to pay them for their individual data contributions in order to satisfy certain properties. It's also used in the context of interpretable machine learning to identify the most important, noisy, or misleading samples in some cases. So these are some of the use cases that are typically mentioned in context of data valuation. But I believe the use cases for data valuation are changing and evolving. So today, there are a number of data marketplaces that are emerging that allow users to post their own data sets. So they choose their own price. And users go on these marketplaces and choose which data sets they want to purchase access to. So examples include AWS Marketplace, Snowflake, DataRaid. And the observation about these data marketplaces is that they typically offer data previews to users. So for example, if I want to purchase this data set on vessel ownership, I could either pay $7,000 or I can check out a free sample preview to decide if I want to purchase this data set. A similar story plays out with a lot of generative data vendors. So a lot of vendors today are selling access to a generative model. For example, Shutterstock is selling stock images. And here you can try a free sample. So you can see a few samples from their generative model before you decide if you want to pay for access to the underlying data distribution, essentially. So an important question that's closely related to data valuation is how should a data user pick the data set that they want to purchase or use? And in some cases, they're not explicitly purchasing it. In some cases, the costs are implicit in terms of what's needed to actually train a model, for example, or conduct your downstream task. So existing data valuation literature tends to be designed to value only a fixed data set. So the effect is that we don't have theoretical guarantees on using the valuation of a particular data set in order to actually value the underlying distribution, which is what we're paying for. The second observation is that existing techniques don't explicitly model or analyze the fact that different data sets are drawn from different distributions. So oftentimes, they'll just compute a data valuation metric without necessarily thinking about what is the underlying distribution that this was drawn from, which means we can't theoretically account for the effects of data heterogeneity, whether that be due to natural randomness or even adversarial inputs from a data vendor. So in this work, we have been starting to consider a problem setting that looks like the following. We have n data vendors, each of whom has their own data distribution, P1 through Pn. And these data distributions can be different from one another in general, so it's a data heterogeneous setting. And each of those distributions has some inherent value, which I'm going to call epsilon. This value is unknown to basically anyone, but we're going to try to estimate it. So from these distributions, what the user actually does have access to is a sample data set. This is like the preview that I told you about earlier. So we sample a data set from each of these distributions. I'm using notation a bit here, saying D, the data set D is drawn from the distribution P1. And these are MIID samples for each of these distributions. Now from these distributions, we can compute a data set valuation, which I'll denote nu of D. All right. Now the data user, which is all of us going on to Snowflake Marketplace to purchase a data set or access to a data stream is going to look at these data set valuations and try to determine which of the data vendors should I purchase from. In other words, we want to choose a distribution valuation function epsilon and a data set valuation mu so that the data user can identify the most useful data vendor based only on the sample data sets that they have access to. Now, of course, the key question is how do we actually define this distributional utility? What does that even mean? And to nail down this problem statement a little bit more carefully, we're going to make an additional assumption, which is that we have access, or no, we don't have access to, but there exists a reference distribution, P star. So this is representing the underlying distribution for the downstream use case that the data user has. So for example, if they're trying to train a model for their own enterprise or whatever, P star would be the distribution of their clients' data. We assume that this exists. We do not assume that we have access to it. And what we're going to do in our model is to think about these data vendors as following a Huber model with respect to this P star, okay? Which is to say, there exists some contamination distribution Q, and the distribution P that the vendor actually draws from is going to be some mixture of this contamination Q and the reference distribution P star. So formally, we'll write this as P is a mixture, epsilon Q times 1 minus epsilon P star. So here, the larger epsilon is, the closer we are to Q. Now, in the context of this earlier problem statement or earlier model, we're going to have these n different data vendors, and each of them can have a different contamination distribution in general. And each of them can also have a different degree of contamination, a different epsilon. Okay, so vendors could be at different points along this. So now, if we go back to this statement of what we want, we're trying to design or choose a distribution valuation function epsilon that is somehow measuring each vendor's closeness to the reference distribution P star. We're going to choose this as a distance measure between distributions, between P and P star. And in particular, we want to choose this epsilon and mu in such a way that we can get theoretical bounds on how different should the data set valuations be in order to conclude that the underlying distribution was also better. And we want that dependence to be explicit in the sample size M and the heterogeneity levels, the epsilon. So to answer this, there's a number of questions that we need to figure out. The first one, of course, is what distance measure epsilon should we use? The second is, once we've defined epsilon or specified it, what valuation mu should we choose? Third is, how do we approximate the reference distribution P star? Because as I mentioned earlier, we don't have access to that. Nobody has access to it. It just exists. And fourth is, how does data heterogeneity affect our data valuation? So let's start with the first question. What distance measure should we use? So the intuition here is pretty simple. The intuition is that the closer we are to P star, the more valuable the data set should, or the data distribution should be. So in this picture, I would prefer P2 to P1 because it is closer to P star. So we're going to restrict ourselves to some kind of statistical divergence between probability distributions, some measure of distance between them. We're just going to take the negative because I want a higher valuation to correspond to a closer data sets. Now here, there's a, yes.
So why not D P star P?
Okay, good question. So in general, I'm not going to require that this be symmetric because P star is playing a kind of an asymmetric role in this whole setup. So I'm going to allow this to potentially be an asymmetric measure. So P star, I just arbitrarily set it as. So when we are trying to choose what kind of divergence should we use, this question starts to look a lot like a question that we ask in the design of generative adversarial methods. So basically, we're trying to measure a distance between two distributions based on samples. And in that literature, there's been a lot of discussion on what distance measure to use. So a lot of work has looked at using f-divergences. So f-divergences here are measuring the distance between these distributions, P and P star, by looking at the ratio of these two densities when they exist, integrating over the space. Now, and some very well-known examples of f-divergences include KL divergence, total variation distance, and these techniques are very widely used in the data valuation literature. A second class that has gotten a lot of traction in the GAN literature is integral probability metrics, IPMs. And these metrics take the approach of instead measuring the distance between these distributions by looking at the difference rather than looking at the ratio. And this has the nice property that even if these two distributions are not defined on the same support, we can still get numbers that make sense. So notable examples include the Wasserstein-1 distance and the maximum mean discrepancy. So a lot of prior works on valuation have focused on f-divergences for their nice theoretical properties. So some of the benefits include a clear information-theoretic interpretation, especially for like KL divergences, for example. And they're also used often to prove some kind of incentive compatibility. So remember I said earlier that data valuation is often used to analyze data markets. So you have different users who are trying to, who are reporting their data and wanting to get some payment for that data. So a lot of the prior work that uses KL divergences or information-theoretic measures are showing that some kind of Nash equilibrium, like you're incentivized to report your data correctly. But of course, there are also some drawbacks, which is that these f-divergences are notoriously difficult to estimate from samples, especially as your dimension increases. So we often, in practice, require variational representations to actually estimate this. And a lot of the prior work on using these divergences requires strong distributional assumptions. So in particular, the assumption that the data vendor's distribution P should be absolutely continuous with respect to P star. And this in general will not hold in a data marketplace data sharing setting.
So you could get around this by using symmetric convergences, like the GSDs would.
Sure, yeah, that's true, that's true. But the estimation properties are still, estimation is still challenging, and you still have this property that if the supports are not equal, the numbers are not as meaningful as several. So yeah, so as I mentioned, this is a similar discussion to what we've seen with regarding GANs, and integral probability metrics are widely used today for estimating distributional distances from examples. We saw this in the very nice keynote this morning, Wasserstein GANs. So in this work, we looked at using an IPM for doing this data valuation task, which is maximum mean discrepancy, MMD. So the MMD was initially proposed as a two-sample test for determining if two sets of samples come from the same distribution or not. So briefly, it's defined as follows, the expression on the screen. So this first term is evaluating the kernel on pairs of samples from the same distribution P. This middle term is evaluating the kernel on pairs of samples from drawn from P and Q. And the last term is evaluating the kernel on pairs of samples all drawn from the same distribution. And so the proposed distribution valuation function that we would like to use is the negative MMD between P, which is the vendor's data distribution, and P star, which is our reference distribution. And we'll see that this choice of epsilon of distribution valuation has some important implications down the line. So given that, let's fix that for now. How do we estimate this from samples? Well, here again, we have a very easy answer, which is that there exist nice estimators for the MMD. So for example, there exists a biased estimator from the work of Gretton and collaborators that basically replaces the expectations in our earlier definition with empirical means. And in particular, the reason we like this estimator is because it comes with uniform convergence bounds. So in particular, let's suppose that we have two data sets, D and D prime, which are drawn from P and P prime respectively. Then this biased MMD estimator, D hat, satisfies the following. So let's parse this. So this first term is the distance between the estimated and the true MMD. So the estimated based on samples and the true based on the distribution. This term depends on our sample size, M, and this beta is just some bias that we can control. And we see that this is decaying exponentially fast in beta squared and in M, the number of samples. So what's nice about this is that this does not depend on problem dimension. So this means that even as our data dimension grows, we still get these nice convergence properties. And that's really important for these kinds of problems. So yes.
In the previous slide, do you assume you have M samples from each, or?
So in general, we can assume that we have arbitrary number of samples from each. I just set them both to M to make this expression simpler.
But and in your work, do you assume you have samples from P star, or that's
We do not assume we have samples from P star, but actually a huge number of papers in this space do assume that we have samples from P star, which I think is not a realistic assumption. So we try to get around that in this work, and I'll touch on it. So sorry, this is a typo. This should be the negative D hat MMD. But the point is, for question 2, we're going to estimate our distribution valuation by using this estimator that already exists. And for now, let's suppose that we can apply it to D star, which is a data set that's drawn from the reference P star. In practice, we don't have it. So in the next question, I'll tell you about how we get around this. All right, so the third question is, how do we approximate this reference D star? As I mentioned, a lot of works just say, well, let's suppose we have it. But in reality, we don't. And so what we do have is these vendors who are drawing from some distribution, P1 through Pn. We don't have D star. So the vendors are exposing their data sets D1 through Dn. So what we're going to do is use a very natural estimate of D star, which is to take the union of all of these data sets, except for the ith one, when we're valuing the ith data set. So if I'm trying to value my data set, I'm going to take the union of everybody else's data as an approximation of D star. And accordingly, we can write a probability distribution P bar of -I that is some linear combination of all of these other PIs. And what's nice about the Huber model of heterogeneity that I introduced earlier is that this can be written itself as another Huber model with a different epsilon-I bar and QI bar. So, and the relevance of this will come back in just a second. So the proposed reference data set that we would like to use here is that instead of using D star, we're going to use D bar -I, which is the union of all of the data sets except the ith one. So finally, let's ask, how does data heterogeneity affect our valuation? So here, recall that we're using for our distribution valuation, the MMD-based valuation, and we are also assuming a Huber model. So under those two circumstances, we can draw on a very recent work by Sherif Abdelatif and Alkier, and which shows that that our data valuation can be written as the negative of epsilon, which was our outlier probability, times the MMD from the outlier distribution to the reference distribution. So this gives a very clear and interpretable understanding of how heterogeneity affects our distributional data valuation. And then we can use our estimator to translate that into guarantees for the samples that we observe. So these are the answers to the 4 questions that I initially posed. So now let's take a look at the main result. So suppose we're given data sets DI and DJ drawn from PI and PJ, and we have a reference data set. So for DI, this would look like D bar negative I, as I mentioned earlier. This result is a little hairy, so let's parse it step by step. Let's start at the bottom, actually. So this is what the buyer wants. The buyer wants to know if the utility of PI is greater than the utility of PJ by some threshold row. That at least row better, is PI at least row better than PJ? Now, what the buyer sees is this inequality. So it's allowed to see the valuation on the actual sample data set. So nu of DI is greater than nu of DJ by some threshold delta. We're saying that if that delta is at least this large, which has 3 terms, first is the desired margin rho. Second is the error from the estimator that I talked about earlier, which depends on sample size and this parameter beta. And the third is this dependence on heterogeneity that I mentioned earlier. Then we can conclude, in fact, that the distribution PI is better than the distribution PJ by some amount. So I wanted to give just an example of how this result might be used and where it fails. So going back to the examples I showed earlier, here, this is a screenshot from DataRaid. Okay, sorry, it's not showing up very well on the screen, but this is an example from a data set that offers a data preview. Now, typically these data previews are on the order of like 10 to 20 samples. They're not that big. So if the data buyer wants to ensure that the valuation on data set I is greater than the valuation on data set J by at least some delta, this was the expression for delta that we had earlier, let's just plug in some kind of back of the envelope numbers. Okay, I'm going to choose 0 for all of the parameters except for the sample size, just to make this as favorable to the data set as possible. And we get a delta of 2.5. Now notice that under our assumptions, the MMD is not going to be ever larger than 2 because we've assumed that our kernel is bounded. So this means that for these small m's, either our bound is too loose to be able to say anything, or these providers should be providing actually more data to allow users to evaluate the difference between data sets. And just intuitively, 10 samples doesn't seem like enough to make any kind of quantitative evaluation of whether one data set is better than another. So I would be inclined to think that it would be useful for these data vendors to provide larger preview data sets. So I also wanted to show some empirical results for this data valuation metric, this MMD-based valuation metric. So to look at this, we constructed some synthetic scenarios where we started with a reference data set, P star, which is the MNIST data set. Then we picked a contamination data set, Q, which is FAMNIST. And what we're going to do is construct a sequence of databases that vary epsilon between 0 and 1. So we know intuitively that the smaller epsilon is, the more valuable that data set should be because it's closer to P star. So we know the true ranking of our databases, or of our data sets, and that's going to be this zeta vector. Then we're going to compute valuations from sampled data sets. And what we want is that our computed valuation should correlate in rank with the true valuation, the ground truth, which we know. So we computed the Pearson correlation here between these two ranked lists. and want this to be as close to 1 as possible. So what we saw is that for both under this Huber model and under other models of heterogeneity and contamination, the MMD was better able to rank these data sets than prior valuation techniques. Now, in the last few minutes, I wanted to discuss a topic that's kind of related to some of the earlier talks. What if we also wanted differential privacy? So in particular, what if we had one data set that we're trying to value against that should be private? So let's revisit the MMD estimator. So this was the expression from before. Now, these red terms are the ones that depend on our private data. And the thing I want you to notice about this is that if I swap out one record from the data set D prime, these terms are could potentially change a lot. So they have high sensitivity. They could affect up to m different terms in the summation for each of them. So because these terms have high sensitivity means we would need to add a lot of noise, which means this isn't necessarily a great candidate for differential privacy. So in some recent work, Charlie and some collaborators from Meta have been looking at a related data valuation scenario from the federated learning context. So the setting here is slightly different. The idea is that we have a reference data set P star, but it's split across a bunch of different federated clients. So that's our reference. And the central server holds a few different pre-training data sets for a model that they want to ultimately fine-tune on the federated client's data. So the question is, which of these pre-training data sets should we choose to best match the distributed federated data distribution P star? Because of some of the shortcomings that we saw earlier with the MMD, in this work, we looked at the Frechet distance, which is commonly used to evaluate generative adversarial networks and other generative models. And we can see that for Gaussian distributions, this Frechet distance takes a very simple closed form expression. So here again, the red terms are the ones that depend on our private data. And what we can see is that this expression only depends on the private mean and covariance of the federated client's data. Unfortunately, this is something that we can estimate easily. We can just have each client add distributed noise and aggregate all of their data, or all of their estimates of these parameters. So empirically, we can get a differentially private estimate of data valuations. And we showed empirically that these data valuations can be used to distinguish very similar data sets and can be also used to predict downstream performance on federated learning tasks like test accuracy. So this plot is showing you an experiment where we had 3 candidate pre-training data sets, which were held at the central server. And our reference data set, which was supposed to be held by the federated clients, was a Stack Overflow data set. So our 3 candidates were some mixtures of Stack Overflow with Wikitext. So Wikitext was like our contamination distribution. And so what we wanted was to conclude that the candidate pre-training data set that consists 100% of Stack Overflow is the best one, has the smallest distance. And so here on the horizontal axis, I'm showing you the percentage of the data set that is Stack Overflow. So basically, this is the one that's closest to the reference data set. And so we want this distance to be smallest. And in fact, we can see that, first of all, it is smallest. And second, it's able to distinguish, even with very strong differential privacy parameters, it's able to distinguish between a data set that is 100% Stack Overflow and 99% Stack Overflow. So this suggests that maybe in practice, we could use some kind of DP estimates of data value or data similarity to choose data sets to pre-seed or pre-train models prior to federated learning. So to summarize, I think that data selection is an important use case for data valuation. And this use case can drive certain desiderata that aren't necessarily analyzed typically in the data valuation literature, including confidence guarantees on when to choose one data vendor over another, as well as privacy guarantees. So I think that MMD can be a useful tool for data valuation, but there's no fundamental reason why it should be only MMD. So there could be other measures that are equally good and give us similar kinds of guarantees. And I think one really interesting open question is to understand if there are trade-offs between valuation and privacy and how to choose what distance metric to use. I think these are really, this is a kind of a messy space. There's a lot going on, and I think there's a lot of room to ask interesting questions around the trade-offs between data valuation and privacy. Thank you all for your attention, and I'll be happy to.
Time for a question. Flo.
Yeah, very nice talk. From the point of view of the person quoting their data or selling their data on the marketplace, they also have an incentive to disclose as little data as possible. So how would that fit into your model? Is there some kind of equilibrium point from like disclosing enough data so someone perceives a high valuation, and how my valuation decreases as I disclose more samples of my data set?
Yeah, that's a great point. In particular, you are incentivized to share fewer samples if your data is bad. So yeah, I think that's a really interesting point and would be a nice way to enrich the model. We didn't analyze that or think about it at all, but I think you're very right.
Yeah, Roy.
I mean, actually, to kind of piggyback on that, I saw I've never seen a paper on it, but I saw work on trying to identify p-hacking or like identify people p-hack by the size of the data that we share.
Okay.
Basically, you're incentivized, like if you're willing to share a lot of data, then it's less likely that you p-hack. So by the larger size of the data that you're sharing, there's you can infer how likely it is that someone's p-hacked.
That's very interesting. I would love to, maybe I'll talk to you later. I'd love to get that paper.
Another question? Let's take the speaker. An hour and a half break and converge at 1:45.
Sure.
Not in mind.